Hey guys, we're going to be going over problems 8 and 9 of the EE301 review packet. Let's get started with problem 8, which is find the Thevenin impedance and the Thevenin voltage of the circuit below, and draw the Thevenin circuit with the load attached. So first step with Thevenin problems is to find the Thevenin impedance. Okay, so how we're going to do that is we're going to remove the load from the circuit, and we're going to redraw it. So we'll take our load out, and we'll redraw this capacitor here. That was negative J8, and then we'll redraw this resistor here, 16. And then remember, current sources become opens. Voltage sources become shorts. So we'll open that current source there. All right, so now we have to find the resistance from the load on the right side. So one thing you'll notice right away is that there's an open in this branch right here. That means that there will be no current flow over here. So this resistor and this inductor are taken out of the equation entirely. There can't be any current flow through here. So all we have to worry about is this capacitor and this inductor and this resistor right here. So that means when we're solving for the Thevenin, we'll just have the capacitor and the resistor in parallel. And that gets us roughly 7.15 at an angle of negative 63.4 degrees. There's our Z Thevenin. Now the next step is to solve for the Thevenin voltage. So we'll put our source back in, redraw the circuit, J10 and 22, and this is 8 at an angle of 30, and we'll keep the load open. So there, and whatever the voltage is at these points is the Thevenin. So one thing we want to do first is we want to take stock of what components are relevant to our Thevenin voltage. So you may notice that the top of the Thevenin voltage is the same as this node right here at the top of the capacitor and the resistor, and that the bottom is connected to the bottom of them. That means that the voltage of these components is the same as the voltage Thevenin. Okay, they're the same because they're all in parallel. So to make the math easier for ourselves, the first thing we want to do is we'll want to combine this capacitor and this resistor in parallel. That's going to save us a little bit of time. So we'll do that. Actually, we already did that before, conveniently. The number's right here, right? Remember, that's not going to be the same in every problem, but coincidentally, we already have that number from the previous part. So the next step is that we will redraw the circuit again. This time, we'll have these combined. We'll use a box this time. And this right here is 7.15 at an angle of negative 63.4. 8 at an angle of 30. And remember that because it was in parallel with the Thevenin voltage, that its voltage will be V Thevenin. So now what we have to do is use Ohm's law, right? We have its impedance, which was coincidentally Thevenin impedance. And we have the current, which was 8 at an angle of 30. So now we just multiply those together with 7.15 negative 63.4 times e to the 30 And that gives us, put in the calculator, 57.2 at an angle of roughly 33 degrees. So the last step is to redraw the circuit, right? So we'll have the same way we always do. We'll have a voltage source with the Z Thevenin, and then the load, which in this case is a resistor and an inductor. So now we can redraw it to more closely match what we had before. Your teacher may want it this way, where you draw your source. Remember, your source voltage is V Thevenin, which in this case is 57.2 at an angle of -33. And then we'll have our Z Thevenin, and we'll have the load, which was a resistor and an inductor. This resistor was at 3.2. This part was at 6.4 J. And the last step is to plug in your V Thevenin. Now, V Thevenin was equal to 7.5 at an angle of -63.4. So what we're going to want to do is we're going to turn that into rectangular form using your calculator, which will give you 3.2 minus J 6.4, or something very close. Now what this does is allows us to separate this into a resistor. And because this is negative, we'll separate this part into a capacitor. So we'll have a resistor here and a capacitor here, and they will have those values. So this will have J 6.4, and this will have 3.2. And this is negative, it's a capacitor. Now that we've got our full Thevenin equivalent circuit, our next question is, this is question 9, is maximum power being delivered to the load? So when you're thinking AC, you have max power when Z Thevenin is equal to the complex conjugate of the load impedance. What does that mean? That means that if the load impedance is some value at an angle theta, the Thevenin impedance is that same value at an angle of negative theta. Is that true? Well, let's see here. We've got the same resistance value and opposite imaginary values. So we will end up, for our load impedance, we'll end up somewhere up here. And for our Thevenin impedance, we'll end up somewhere down here, totally opposite angles. And if you put these in your calculator, you'll see that they're entirely opposite. This number right here, -63. This number here becomes 7.15 at positive 63.4. So they are the exact opposite, which means, in terms of angles anyway, which means that we, yes, do have maximum power being delivered to the load. And that is number 8 and 9 on the EE301 12-week review packet. Thank you.